Welcome to the Deep Dive. Today, we're tackling a topic that's really kind of bubbling up in chemistry and industry circles. Solvents.
Mm-hmm.
For decades, we've relied pretty heavily on traditional organic solvents, right? But their downsides, environmental impact, safety concerns, that's really pushed the search for cleaner options.
Absolutely. People are looking for greener ways to do things.
You've probably heard of some like room temperature ionic liquids, maybe supercritical fluids. Those are examples. But today, we're going to plunge into another really fascinating category: deep eutectic solvents. D for short.
Exactly. And what makes DS so interesting, I think, is that they're usually formed by just mixing two or more solids, things that are solid on their own.
Right.
But when you combine them in just the right ratio, they spontaneously turn into a liquid at room temperature often. It's almost like a bit of chemistry magic, solids in, liquid out.
Yeah, it does sound a bit like that. So our goal today for you listening is to really explore these deep eutectic solvents thoroughly. We're planning to go through our source material chapter by chapter, sort of building up a solid understanding, looking at the fundamentals, and then the really exciting ways they're being used.
Sounds like a good plan.
Okay, so with that mapped out, let's just jump straight into chapter 1. This really lays the groundwork, explaining why DS are, such a big deal.
Right. Chapter 1, it really hammers home the absolutely essential role solvents play pretty much everywhere in chemistry.
You mean in labs and industry?
Yeah, exactly.
Yeah.
From the really meticulous work in research labs all the way up to, massive industrial production scales. Just think about it. Almost every chemical reaction, every separation process, it needs a solvent.
To dissolve things.
To bring reactants together so they can actually react, or, to dissolve something so you can isolate the product you're actually after. They're fundamental.
And that brings up, a critical point you mentioned earlier. What actually makes a solvent green? It's more than just a buzzword, I assume.
Oh, absolutely. It's not just a label you can slap on anything. A truly green solvent has to tick several important boxes.
Right.
Well, first off, it needs to be environmentally benign. Safe for ecosystems, safe for human health. It shouldn't just hang around in the environment causing problems, and it shouldn't be toxic.
Okay, non-toxic. Makes sense.
Ideally, non-toxic and readily biodegradable, meaning it breaks down naturally into harmless stuff. And then, from a practical angle, it needs to be easy and cost-effective to make.
Right, using things that are easy to get hold of.
Exactly. Readily available, low-cost starting materials.
Yeah.
That's key for it to be actually adopted widely.
Those are some really clear benchmarks. Okay, now, that term deep eutectic, the deep part, it suggests there's something more going on than just, mixing two things together. What's the science there?
Yeah, the deep bit refers to a really significant drop, a depression, in the melting point of the mixture compared to what the individual components melt at.
Lower melting point.
Much lower, often. And this is where solid-liquid phase diagrams become really important. Picture this. You have two solids, right? Each melts at its own, probably quite high temperature.
Okay.
But when you mix them in a very specific ratio, that's the eutectic composition, the way the molecules of the two components interact with each other actually disrupts their nice ordered crystal structures.
They interfere with each other's freezing.
Pretty much. They get in the way of each other, forming a solid lattice. And the result is a mixture that melts at a much, much lower temperature than either of the starting solids could on their own. Chapter 1 actually gives a closer look at these diagrams and how they figure them out. It really illustrates how these molecular interactions lead to this surprising liquid state. It's all about understanding that interference.
That's a fantastic explanation. So by picking the right components and mixing them in the right proportions, we're basically designing liquids that exist at room temperature and hopefully have useful properties. Okay, let's move to chapter 2 then. This promises to show off the impressive variety of DS that people have come up with.
And impressive really is the right word. Chapter 2, it dives into just how many different combinations can form these liquids at, normal conditions.
Ambient conditions.
Right. And while also meeting those green criteria we just talked about, it's definitely not a one-size-fits-all kind of thing. It's a huge landscape of different possibilities.
One type that jumped out at me was UNAIDS natural deep eutectic solvents. That sounds particularly good from a green perspective.
UNAIDS are fascinating, yeah. The key thing about them is that their components are naturally occurring substances.
So from plants or animals?
Exactly. Things like sugars, amino acids, organic acids found in nature. This often means you don't need complex chemical synthesis to get the building blocks. You can derive them directly from biological sources. which, aligns perfectly with those green chemistry principles, using renewable resources.
It's almost like nature had its own green solvents already.
In a way, yeah. Seems these mixtures play roles in biology, too, which we might touch on later.
Interesting. Now, the chapter mentions a sort of benchmark DS, the 1:2 mix of choline chloride and urea. Reline, it's called. That sounds like a key example.
Absolutely. Reline is often called the prototypical DES. It's one you can actually buy commercially. It's relatively simple to make. And its discovery back in 2003, well, that really kicked off the explosion of research in this area.
Is it breakthrough?
A huge one. And a lot of the DS developed since then are based on choline salts or similar sorts of molecules. It just shows how effective that type of structure is as a hydrogen bond acceptor, one part of the puzzle in forming these eutectic mixtures. Reline really is the cornerstone for a lot of this field.
So Reline is kind of the original blueprint, but what about these conventional DS the chapter mentions? What are the typical ingredients for those?
Right. Conventional DS, they usually involve a salt component, often an organic salt, like an alkyl substituted ammonium, or maybe a phosphonium salt,
Okay, salt plus something else.
plus a hydrogen bond donor. That's the other key piece. This donor is frequently something like an amidite, or maybe a molecule with hydroxyl groups, OH groups. So things like simple alcohols, polyols, glycerol is a common one, or even carboxylic acids.
And the ratio matters.
Critically.
Mm.
The specific molar ratio between that salt and the hydrogen bond donor is what determines the exact eutectic point, the composition where you get the biggest drop in melting point.
Got it.
And what's interesting is because they contain these salts, these conventional DS are actually considered a subgroup of ionic liquids, those room temperature molten salts we mentioned at the start.
Ah, so there's an overlap there.
Yeah, there's definitely connection and overlap between these different classes of neoteric or modern solvents.
Okay, so we're seeing how these different solvent types relate. The chapter also brings up unconventional DS. What makes them unconventional?
Unconventional DS really broaden the scope of what you can make these liquids from. They might involve components you wouldn't immediately expect.
Like what?
Things like metal salts, for instance. Even metal salt hydrates, where water molecules are actually part of the salt's crystal structure. Or even zwitterionic amino acids, those molecules that have both a positive and a negative charge on the same molecule.
Wow, okay, so quite different building blocks.
Very different. But despite this variety in the ingredients, these unconventional ones also tend to be ionic in nature. Using these components opens up possibilities for DS with potentially very different properties and uses compared to the more common ones based on organic salts.
That's a surprisingly wide range of ingredients. And then there are non-ionic DS. How do they fit in if the usual definition involves ions?
That's a great point, and it shows how the field's understanding has evolved a bit. While the early focus was often on having an ionic part, researchers realized that you can get similar effects, that deep melting point depression, even without formal ions.
Through hydrogen bonding.
Primarily, yes. Strong intermolecular interactions like hydrogen bonding are still key. These non-ionic DES usually involve mixtures like sugars combined with carboxylic acids. You might also see them called LTTMs, low transition temperature mixtures.
LTTMs.
Yeah, it reflects their generally very low ionicity and consequently low electrical conductivity. But the remarkable thing is they can still be really effective solvents, especially for things like enzymatic reactions.
Why enzymes?
Well, sometimes a highly ionic environment can actually mess with an enzyme's structure or function. So these less ionic LTTMs can be gentler, more compatible environments for biocatalysis while still offering the benefits of being a liquid mixture formed from solids. The key is still achieving that significant melting point drop.
It's really fascinating how mixing different kinds of solids can lead to this liquid state just through their interactions. All right, let's dig into chapter 3 now. This one explores the actual properties of these deep eutectic solvents. I guess understanding their characteristics is absolutely vital for figuring out where they're going to be useful, right?
Absolutely. Chapter 3 is where we get down to the nitty-gritty. What defines a specific DES? What makes it suitable for one job versus another? It really comes down to this complex interplay of their physical and chemical properties. That's what dictates performance.
The chapter kicks off by revisiting solid-liquid phase diagrams briefly. We touched on why they're important for finding the eutectic point, but why else are they relevant when we talk about properties?
Well, the phase diagram isn't just about finding that sweet spot, the exact composition and lowest melting point. It gives you a much bigger picture. It shows how the mixture behaves over a whole range of temperatures and compositions. This is crucial for understanding things like the DES's thermal stability. How hot can you get it before something goes wrong? What's the temperature window where it actually stays liquid? And how might its properties shift if the temperature or composition changes slightly during a process? Think of it as a kind of operating manual or a map for the liquid state of that specific DES system.
That makes perfect sense. It defines the boundaries of where it works as intended. Okay, let's talk thermodynamic properties. The chapter lists things like vapor-liquid equilibria, solid-liquid equilibria, heat capacity, surface tension. Can you give us a quick rundown on these for DES?
Sure. So vapor-liquid stuff.
Sure.
A really key advantage of most DES is their incredibly low volatility. They just don't evaporate easily.
Low vapor pressure.
Exactly. Very low vapor pressure, and that's a massive plus, both for safety, fewer flammable or harmful vapors, and for the environment. You're not losing your solvent to the atmosphere.
That's a core green aspect then.
Definitely. Solid-liquid equilibria, as we said, define that temperature range where it's liquid. Heat capacity that tells you how much energy it takes to heat the DES up or cool it down. Important if you're designing a process that involves temperature changes.
Right, for energy efficiency.
Precisely.
Yeah.
And surface tension that affects how the DES interacts at surfaces with other liquids or solids. It's important for things like making emulsions, coatings, or in extraction processes where you need good contact between phases.
Does the chapter give examples?
It does. It mentions, for instance, that the surface tensions for choline chloride mixed with urea, this reline, and with ethylene glycol are around 52 and 49 millinewtons per meter, respectively, at 25 degrees C. And it even gives data on how that changes with temperature. So quite specific data is becoming available.
That low volatility really does sound like a game changer. Okay, moving on to transport properties. Viscosity seems like a really big one for how a solvent actually functions. What does Chapter 3 tell us about DES viscosity?
Viscosity is hugely important, yes. It basically governs how easily things can move around within the solvent.
Like molecules dissolving or reacting.
Exactly. How easily solutes dissolve, how quickly they can diffuse to meet each other for a reaction, so it affects reaction rates, mass transfer, and it also strongly influences electrical conductivity. If ions can't move easily because the liquid is too thick, the conductivity will be low.
Which matters for electrochemistry.
Right. Now, generally, like most liquids, DES viscosity goes down as you heat them up. They get runnier.
Okay.
And the chapter notes this temperature dependence often fits mathematical models, like the Vogel-Fulchertaman, the VFT equation, or sometimes a simpler Arrhenius expression. Table 3.9 in the source actually lists viscosity values at 25 degrees C for a bunch of different choline chloride-based DS.
But you said earlier the values can vary.
Ah, yes, that's a crucial point. You might see different viscosity values reported in the literature for what seems like the same DES. And a major reason for this variability is often the water content.
Water. Even a little bit.
Even small trace amounts of water can significantly lower the viscosity of many Ds. They're often quite hygroscopic. They absorb moisture from the air. So careful sample preparation and reporting water content is really important for getting reliable, comparable data.
That's a really practical detail to be aware of. What about other physical properties mentioned, like refractive index or permittivity?
Yeah, refractive index, that's about how light bends when it passes through the DES. And permittivity relates to how the material stores electrical energy when you put it in an electric field. Both are useful properties.
How so?
They give you more information about the DES itself, its interactions with light and electric fields. Refractive index, for instance, can be a quick way to check the purity or composition of a DES, almost like a fingerprint. Permittivity influences how well the DES can dissolve ionic compounds, for example. Table 3.15 is mentioned as having refractive index data for various Ds.
Okay, useful characterization tools. Now let's dive into the chemical properties. This looks like a big section. We've got liquid structure, solvatochromic indices, acidity, basicity, hydrophilicity, gas solubility, electrochemical properties? Wow, where do we start?
Yeah, it's quite a list, covering how the DES behaves chemically. Let's start with liquid structure. This is about understanding how the molecules or ions in the DES are actually arranged at a microscopic level.
How do they figure that out?
They use really advanced techniques. Computer simulations, like molecular dynamics, are huge. They model how all the individual molecules interact and move over time. And experimental methods like neutron diffraction can give direct information about the distances between atoms.
Any specific examples?
The chapter mentions simulations done on reline, choline chloridurea, and also on the choline chloride ethylene glycol mixture. These studies have provided really detailed pictures of how the choline cation and the chloride anion are surrounded by the urea or ethylene glycol molecules, and especially mapping out the network of hydrogen bonds that holds the whole thing together. That hydrogen bonding network is key to their structure and properties.
So understanding the structure explains the behavior. What about solvitochromic indices? That sounds technical.
It's basically a way to measure the solvent's polarity and its ability to interact with dissolved molecule solutes in different ways. They use special dyes that change color depending on the solvent environment.
Ah, solvitochromic solvent color.
Exactly. Parameters like ETN or the Camelot-Tap parameters, alpha, beta, pi star, quantify these interactions. The chapter points out that DS generally falls somewhere between methanol and water in terms of polarity.
More polar than many organic solvents, then.
Often, yes, and comparable in polarity to many room temperature ionic liquids. These indices basically give you a fingerprint of the solvent's interaction capabilities with stabilized charge as well. Is it a good hydrogen bond donor or acceptor? This helps predict how it will behave in reactions or extractions.
Okay. Acidity and basicity, how is that measured in a DES?
It's often described using apparent pH values, as shown in Table 3.19. It's not exactly the same as pH in water because it's a non-aqueous system, but it gives an indication of the DES's proton donating or accepting ability, which is obviously critical for many chemical reactions.
Right. And hydrophobicity, does it mix with water or oil?
Pretty much. This determines its miscibility, whether it mixes easily with water or with nonpolar solvents like hexane. Crucial for designing separation processes like liquid extraction. You need phases that don't mix completely.
Makes sense. Gas solubility, we touched on CO2 and SO2 earlier. This seems like a hot topic.
It really is. The ability of some DS to dissolve gases, particularly CO2 and SO2, is driving a lot of research for environmental applications, like carbon capture from flue gases or removing sulfur dioxide. Tables 3.21, 5.4, and 5.5 provide specific data, like Henry's law constants, which quantify how much gas dissolves under certain conditions.
Okay. And finally, electrochemical properties.
This is vital for using DS in things like batteries, capacitors, or electroplating. Key properties include the electrochemical potential window, the EPW.
What's that?
It's the voltage range over which the DES is stable. If you apply a voltage outside this window, the DES itself starts to break down, oxidize, or reduce. So a wide EPW is usually desirable. Table 3.20 lists EPWs for some DS. Other things like ionic conductivity and double-layer capacitance are also important for electrochemical device performance.
Wow, that's a really thorough breakdown of the chemical characteristics. And the chapter wraps up with a really crucial point: toxicity and biodegradability. We labeled them green, but are they always environmentally friendly in practice?
That is such an important question. And the straightforward answer is, it depends. It really varies depending on the specific components used to make the DES.
So not all DS are equally green.
Exactly. While many of them, especially the NEs derived from natural sugars or amino acids, are generally considered to have low toxicity and be readily biodegradable, that's not universally true for all DS. Research highlighted in the chapter has looked at the toxicity of various DS towards different organisms, bacteria, brine shrimp, cell lines.
And found differences.
Yes. Some DS, perhaps those containing certain types of cations or longer alkyl chains, can show higher toxicity. Studies on butane-based DS, DTES, and natural switterion are also mentioned. The bottom line is you can't just assume a DS is harmless because it's called a DS. Each specific formulation needs a proper toxicological and environmental impact assessment.
That's a really critical nuance. No free passes just because it's a DES.
Okay, so we've built a solid foundation now, fundamentals, properties. Let's switch gears in Chapter 4 and look at the applications. Since they popped up in 2003, it sounds like they've really taken off.
They really have. It's been less than 2 decades, relatively speaking, but the range of applications is already huge. Their ability to dissolve so many different types of substances, combined with those green characteristics we keep mentioning, has just unlocked potential everywhere. Chapter 4 really showcases this versatility.
A major area seems to be using them as reaction media, as the solvent for doing organic synthesis. What's the advantage there? Why use a DES instead of, say, toluene or water?
Several potential advantages. DES can sometimes speed up reactions or make them more selective, meaning you get more of the product you want and less of the unwanted side products.
Better yields, cleaner reactions.
Potentially, yes. Also, in some cases, the DES isn't just a passive solvent. It can actually participate in the reaction, maybe acting as a catalyst itself. That simplifies things.
The solvent is the catalyst. It can happen. Plus, they're often compatible with enzymes, which opens the door to biocatalysis using nature's catalysts in these novel solvents. Table 4.2 gives concrete examples, using reline for bromination reactions or using lipase enzymes to make esters like butyl, valerate, and various Ds.
Interesting.
Another cool example mentioned is using Ds to help produce cellulose nanocrystals, tiny, super strong rods derived from cellulose, which have all sorts of potential uses in advanced materials. So understanding those properties we just discussed, low volatility, polarity helps explain why they work well here.
It's fascinating to see the solvent taking such an active role.
Okay.
Another big area mentioned is biomass and biodiesel. How are Ds helping make fuels and chemicals from plants?
Right. Biomass, think wood chips, straw, that kind of stuff. It's mostly cellulose, lignin, hemicellulose, all tangled together. It's tough stuff.
Hard to break down.
Very. DS, and also related systems like molten salt hydrates, have shown a remarkable ability to dissolve or at least swell and pretreat this lignocellulosic biomass. They can disrupt the rigid structure, particularly the cellulose part, making it much easier for enzymes or chemicals to access it later and break it down into useful sugars or other building blocks.
So a key step in biorefining.
Exactly. Table 4.3 lists some specific salts and DS used for this. Then for biodiesel, DS are being explored as catalysts for the key reaction, transesterification, which turns vegetable oils or animal fats into biodiesel. Table 4.4 shows different deassing as catalysts, potentially offering a greener way to make biodiesel compared to traditional methods.
So really contributing to renewable energy and materials, the chapter also talks about metal electrodeposition and electropolishing. That seems like a totally different field.
It is, but it connects back to the property of some DS being able to dissolve things you wouldn't expect, like metal oxide. Because certain Ds, notably reline and ethylene, choline chloride-ethylene glycol, can dissolve metal oxides, they can be used as the electrolyte bath for electroplating metals onto surfaces, or for electropolishing, basically smoothing metal surfaces electrochemically.
Instead of using harsh acids or cyanide baths.
Potentially, yes. It offers an alternative that might be safer and more environmentally friendly. Tables 4.5 and 4.6 give examples of different metals being deposited or polished using these DS-based electrolytes.
That really underscores the versatility biofuels 1 minute, metal finishing the next. And then nanotechnology. How are DS being used at the nanoscale?
Nanotechnology is another really active area. DS are proving useful in making all sorts of tiny materials.
Like what?
Nano-sized metal particles, gold and silver nanoparticles are mentioned, magnetic iron oxide nanoparticles, FF304, things like carbon nanotubes and graphene sheets, even specialized materials like molecularly imprinted polymers.
How do the DS help make these?
Often, the DICIA acts as more than just a solvent. It can serve as a template, guiding the formation of the nanoparticles, or as a stabilizing agent, preventing the tiny particles from clumping together. The chapter gives specific examples, like making gold nanoparticles in reline, or those magnetic iron oxide particles in different choline chloride DS. The DS environment influences the final size, shape, and properties of the nanomaterial.
It's incredible the breadth of applications, from bulk chemicals and fuels right down to manipulating single atoms and molecules. Okay, let's move to Chapter 5. This one zooms in on using DS in extraction and sorption. Sounds like separation science.
Exactly. Chapter 5 is all about using DS to separate things, purify mixtures. Their unique properties make them really good at selectively grabbing specific molecules out of a complex mix.
One application mentioned early on is desulfurization and denitrification of fuels. So cleaning up gasoline or diesel.
That's the idea. Sulfur and nitrogen compounds in fuels are big contributors to air pollution, acid rain, smog. Certain DKIs have shown they can selectively pull these compounds out of the fuel. It comes down to specific interactions. The components of the DES interact more strongly with the sulfur or nitrogen molecules than with the fuel molecules themselves, effectively extracting them. This could lead to cleaner burning fuels.
A potentially significant environmental benefit. The chapter also mentions extracting hydrocarbons and oils. Can DS separate different types of oils or fuel components?
Yes, that's another area. For example, separating aromatic hydrocarbons, like benzene rings, from aliphatic hydrocarbons, straight chains, is a standard process in refining. DS are being explored for this. The example given is using malene, that's choline chloridomalonic acid, to pull ethanol out of a mixture with N-hexane.
So you can tune the DES to grab what you want?
That's the key advantage. By choosing the right hydrogen bond donor and acceptor, you can tailor the DES's properties to have a higher affinity for the specific compound you want to extract.
Clever. What about getting valuable things out of natural sources or removing unwanted metals?
Right. DS are being looked at for extracting metal ions, maybe for recycling metals from e-waste, or for cleaning up water contaminated with toxic heavy metals. And on the natural product side, especially NADs, they're showing real promise.
Like getting antioxidants.
Exactly.
Huh.
The example cited is using sodium acetate-based LTTMs, remember, the non-ionic ones, to extract antioxidants from grape pumice, which is a waste product from winemaking. It offers a potentially greener way to get these valuable bioactive compounds compared to using traditional organic solvents.
Turning waste into value using a green solvent. Nice synergy. Okay, the last part of this chapter is about sorption of obnoxious gases CO2 and SO2 again. This links back to their gas solubility properties.
It does, because some DS can absorb quite large amounts of these gases. They're being seriously considered for gas capture technologies.
Like scrubbing CO2 from power plant emissions.
That's one major target, yes. Or removing SO2 to prevent acid rain. Tables 5.4 and 5.5 are referenced again, showing the capacity of DS like rhyline and collinium acetate for these gases. An important practical point mentioned is that water content can sometimes reduce the CO2 absorption capacity, so that's something to manage in real-world systems.
Still, a really critical area for tackling air pollution and climate change. Okay, we've covered a lot of ground. We're now at the final chapter, chapter 6, which looks forward, trends, future prospects for DS. Where does the field seem to be heading?
Chapter 6 paints a really optimistic picture, I'd say. A big theme is their growing role in sustainable chemistry overall.
How so?
Well, the potential to replace hazardous traditional solvents is huge, using them to process renewable, non-fossil raw materials like that biomass we talked about, designing processes that minimize waste, improving catalysis, maybe even using the DS itself as the catalyst more often. It's all about making chemical processes greener and more efficient.
So really fitting into that push for a more sustainable circular economy, what other specific areas look particularly promising?
Material science and nanotechnology are definitely going to keep pushing forward, building on the kinds of synthesis examples we saw. Analytical chemistry is another area using DES for preparing samples or in analytical techniques themselves. And certainly improving those sorption and extraction technologies for industrial separations and environmental cleanup.
And new types of DES.
Oh, yes. The development of unconventional DES using different salts, different donors, maybe even metal-based ones, is expected to keep expanding the possibilities and creating solvents with unique, tailored properties.
The chapter also had that intriguing point about natural desnades and their connection to biology. That seemed quite profound.
It really is remarkable. It seems nanades aren't just lab curiosities. They might actually play vital roles inside living organisms.
Like what?
Things like acting as natural antifreeze cryoprotection, helping organisms survive freezing temperatures. And there's evidence that they're involved in how plants dissolve and transport substances that don't dissolve well in water. It suggests these eutectic mixtures are actually a fundamental part of biochemistry and physiology in ways we're only just starting to appreciate.
That's amazing. It completely reframes them, almost. So wrapping it all up, it feels like deep eutectic solvents are this incredibly versatile, really promising class of green solvents. Their potential impact seems huge.
Absolutely. From making chemicals and materials to producing energy to protecting the environment, the BLs offer this tunable, often safer, more sustainable alternative to what we've used traditionally. The continued research and development and hopefully wider adoption could really drive big changes in green chemistry and technology.
This has been a genuinely insightful deep dive. It really opens your eyes to the potential packed into these seemingly simple mixtures. It makes you wonder, doesn't it? What other surprising roles might these eutectic liquids play, not just in our labs and industries, but maybe hidden in plain sight in the natural world all around us? Something to think about. Thanks for joining us for this exploration. Until our next deep dive.